Okay, so in physics or in any science, first thing we've got to do is give ourselves what I call rules of thumb. Because a lot of the problems we've been doing since we were in third grade. Yeah, they didn't call it physics in third grade. They called it a nasty thing that we called a word problem. And the word problem would be Joey the giraffe was walking at 3 meters per second for 10 seconds. How far did Joey go? Okay, we've all heard those lovely word problems. Well, I just gave you a physics problem. I just gave you a speed. Joey the giraffe was walking at a speed of 3 meters per second. And we're going to actually use the term speed because we didn't tell you that Joey the giraffe was walking east or west or north or south. We just gave you a magnitude. The magnitude was 3 meters per second. We told you that Joey was traveling for 10 seconds, and then we asked you, how far did Joey the giraffe go? So if we did our 3 meters per second, and we know that we did this for 10 seconds, we know that we're going to end up with 30 meters. And that was our classic word problem that we got in the third grade, that it was 3 times 10 gave us 30. Now, one of the things that I just did that really makes us start going into more science, and a lot of you have already had chemistry, because usually what people do is they take chemistry first, then they take physics. And so one of the things that your chemistry instructor would have probably beat on you about is that numbers have units. So we gave our units here, and we gave ourselves meters, and we gave ourselves seconds. And I can look at what we call dimensional analysis or unit analysis. Or unit analysis. And that tells us that if I have my seconds and I cross out my seconds and I end up with meters, that if we were looking for a distance, I've got a number that's got the right units. It has the right units of a distance. This was a speed, and this was time. So speed times time is going to give me distance, and I can use my units to make sure I did it correctly. So I'll do a common one that we do in chemistry. We do density, right? We say that density is equal to mass divided by volume. And we all know that sometimes when we're trying to solve it, we get something weird, and somebody will do this inevitably. They'll say that we've got a volume over a mass, but if my density is going to be in kilograms per meters cubed, but if I did a calculation and I got meters cubed over kilograms, we know we did something wrong. We didn't get a density because my units needed to be a mass unit divided by a volume unit. So we do dimensional analysis. So you're going to get some problems in the homework in this first chapter that will say, all right, I have a velocity times time, and it's going to ask you if that velocity times time is equal to an acceleration. Well, velocity is going to be in meters per second, or in a length divided by time. Time is going to be in time, but acceleration is a length per unit time per unit time. So that's going to give me a unit of length divided by a unit of time squared. And if I do length divided by time times time, that's not equal to length divided by time squared. So you're going to get a couple of homework problems that they're asking you to do this evaluation. They're looking to say, did I write this formula correctly? In that, do the units on this side match up with the units on that side? They're not expecting you to understand if that formula is really right or not. They're not asking you to understand what that formula means. All they're doing for that homework problem is they're asking you to do this dimensional analysis to see whether or not we got the right units. Because if I check and follow my units, 9 times out of 10, that's going to tell me, did I make an algebra mistake? Did I divide when I should have multiplied? Did I subtract, can I really subtract those two items? Because remember, we can't in mathematics. So if I did a velocity times time plus a distance has to equal to a distance, this is meters per second times seconds. This is in meters. This equals meters. Well, if I do that, I get meters plus meters equals meters. I can add those together because I can add apples to apples, but I can't add apples to oranges. So this is a way to tell, did I forget a square? If I've rearranged my equation at some point, did I forget a square? And being able to do this dimensional analysis is really gonna help you out and allow you to double check. And 9 times out of 10, when I'm looking at partial credit, I'm looking to see, did you get meters plus meters is equal to meters? And I am not going to be so worried about, did you get fumbled fingered and punch in the wrong number in your calculator? So that's one of the things that's there, because I'll see that, because if you're in the middle of a test or a quiz, we all know sometimes you forget the square. Or you hit the calculator and you thought you hit the square button, but the calculator didn't actually square the value. So really, I'm not going to look for fumble fingers on the calculator. I'm looking, did you get the equation correct? Did you do the evaluation of the equation correct? And have you got the right units to play with? So that's what I'm looking for, because this is going to save your hide 9 times out of 10. 9 times out of 10, because what most of you will do is you will talk yourself out of the right answer. I see it all the time, because you go, well, that wasn't that hard. Physics is supposed to be hard. So if physics is supposed to be hard and I got that answer real quick, maybe I did something wrong. No. Did your units work out? Does the number seem reasonable? You probably didn't do it wrong. So don't talk yourself out of the right answer. So let's look at a couple of other things, because then we start talking about conversions, because we're always going to have to do conversions. And the reason we're going to have to do conversions is we want to add meters to meters, not meters to feet. So we've got to do conversions. Now, here's a secret. Chemistry is all about conversions. If you figured out that chemistry was about converting mass to moles, moles to grams, grams to moles, you were leaps and bounds ahead of everybody else in chemistry class. It's all about conversions. So most of us are used to doing conversions. We do conversions a lot. So conversions are things that we're going to use our numbers with. And we have lots of conversions in our head, right? There are 12 inches is equal to 1 foot. We know that 3 feet is equal to 1 yard. We know that 100 meters is equal to, what is it, a decimeter? Let's go ahead and do 1,000 because it's late in the day. So 1,000 meters is 1 kilometer, which is why we really like the metric system. We really like the metric system. However, when we're doing physics problems, those rules of thumb kick in. So if I were telling you that a car was going down the street at 50 meters per second, most of you wouldn't have a clue as to whether or not that was reasonable or not. 50 meters per second doesn't necessarily, that's not in your head. But if the car was going down the street at 50 miles per hour, you'd go, yeah, that's a reasonable, depending on where we're going, we're not going through a school zone. But depending on where we're going, we can say whether or not that 50 meters is reasonable or not. Well, here's a rule of thumb that we want to get stuck in our heads pretty quickly. It's the number 27. 27 meters per second is approximately 60 miles per hour. So that's going to give you a way to look at the problem when you've done your calculation. Is something reasonable? You know, we sit there and we think to ourselves, all right, I'm in the basketball game and and the person shot the basketball 20 feet. Well, that's a reasonable number in a basketball court because we have an idea in our head what's the size of a basketball court. What we don't necessarily have in our head is what's the size of an acre. So we've got to get those things kind of in here. One of the things that you want to look at, and that's why I wrote down 100. 100 meters is roughly 100 yards. 1 yard is roughly a meter. 2.54 centimeters is equal to 1 inch. Okay. So if we wanted to do a conversion, so I'm going to do 5280. And hopefully most people know what 5280 is. 5280 is feet in a mile. But I want to know how many centimeters 5280 is. I'm going to have to do a conversion. So first thing I want to do is I can go into an app on my phone and figure it out. But if I'm in physics class and I'm told and I'm going on to the MCAT, some of you may be taking the MCAT, and I don't know if you've heard, but there are certain sections of the MCAT now that you're not supposed to have your calculator with you. So I'm going to have to do this without my calculator. And I didn't bring my calculator into class tonight. I have my cell phone if we need to calculate something, but I can add that, but that's one thing. But I'm going to want to do this, so I'm going to have to remember some of my conversion factors. So one of the things I want to do is I'm going to do 12 inches is equal to 1 foot. And I want my feet, so they're going to cancel each other out. But we all know that this is equal to the number 1. So I can multiply any number by 1. All I'm going to be doing now is changing units and doing a conversion. That's all I'm doing. Well, I just gave you what the conversion factor for centimeters is. It's 2.54 centimeters is equal to 1 inch. That's also a number 1. And these are numbers that I am not going to be able to do in my head, especially not at this time of night. So I'm going to get my calculator out. I'm going to get my cell phone calculator out. Okay. Because it's here and we're in a good spot tonight, let's go ahead and look at this. These are I use an Android phone. So these are some of the tools. This is the Firefox app that we will be using a lot, but there are some other handy dandy lab tools on here. I have bubble scales, which are really, really slick. I have measuring devices. I have a simple calculator and I have a complex calculator here. So we're going to use this one. So I've got my 5280 times 12 times 2.54. And that's going to give me, it looks like it gives me 160,934.4 centimeters. Now, if we were in chemistry class, I would probably growl. I'm even going to growl a little bit in physics class because of that lovely thing called significant figures. This was a raw calculation. This was an exact So legitimately, I could say that that number is actually a real number and it's probably okay for significant figures. But if we remember our rules for significant figures, I started with 3 significant figures here because that 0 was a placeholder. This is an exact number because we do know that that happens to be an exact number. But I probably want to have my answer in 3 significant figures. So I would probably want to write down my number as 161,000 centimeters. In my materials and in your textbook and in every chemistry textbook out there, you're going to be dealing with, okay, significant figures gets us to accuracy and precision. And in chemistry, accuracy and precision is really, really great. Even in physics, accuracy and precision is really, really great. But we're in general physics. Most of the time, we're going to be using estimates of 9.81 meters per second squared as our acceleration due to gravity. So most of the time, you're really only going to have to worry and put your answer into 3 digits or 3 significant figures. Most of the time, we're going to be able to get away with that. There are some homework problems that are going to be very specific because we are wanting to show you a specific thing where it's going to ask you to put your answer into 4 significant figures. One of which is the one in this first homework assignment. So I'm going to look it up here just so I have it because I don't remember the number off the top of my head. So the speed of light is 299,792, 458 meters per second. Okay. Well, I want to write this as 2 significant figures. I'm going to write this as 3.00 times 10 to the 8. Actually, that's 3 significant figures. This is 3 significant figures. Because remember that any number that I write in scientific notation is going to be the exact numbers, 3 significant figures. When I write this in WebAssign, what I'm going to write in WebAssign is 3.00. I'm going to use the letter E to the 8. And WebAssign is going to like this. WebAssign won't like this. WebAssign likes this. So now if I want to write this to 4 significant figures, I'm going to write 2.998 e to the 8. And WebAssign will like that. So this is a formatting issue in the WebAssign. So don't necessarily use up all your attempts in WebAssign. If you think it is a formatting issue, please use your Ask the Instructor in WebAssign. Please use the ask, or please email me and say, hey, I think I've got this answer right, but can you look to see if it's a formatting problem? Because I don't want you to get frustrated with WebAssign dealing with formatting when it fundamentally is something as simple as you just didn't type it in the way WebAssign accepts it. So we want to do that. But this is also a fun thing. So what we're going to do is we're going to find out, we're going to ask ourselves a question: how far does light travel in 1 nanosecond? 1 nanosecond. That's 1 times 10 to the minus 9 seconds. We're going to multiply that times, we're going to go ahead and do our 2.998 e to the 8 meters per second. Should be able to do it in my head, but I'm going to double check, make sure I'm doing everything okay. 1. Gives me 0.2998 meters. Or that gives me 29.98 centimeters. I happen to have a ruler here. It's 29, so it's right at. This is a nanosecond. That is the distance that light can travel in a nanosecond. It's roughly the length of the diagonal of a piece of paper, of a diagonal of an 8.5 by 11 piece of paper. So that gives you another rule of thumb to kind of think about playing with information there. All right. Questions so far? Most of this stuff you've seen before. Most of this stuff you played with before. It's just remembering. All right. So let's do an estimate. In the videos that I have provided you an estimate about teaspoons in the ocean compared to atoms in a teaspoon. I think I have an estimate out in YouTube about the number of basketballs that go over Kaw Lake Dam. I know I have done an estimate of number of pineapples in a storage container. Those are always fun. So there's lots of different estimates that we can use. We can use the number of breaths in an hour. We can use the number of heartbeats in a week. But let's do, for grins and giggles, let me think of one that could be fun at the moment. I usually do gumdrops in an Erlenmeyer flask. That's always a fun one too. Oh, trying to come up with one. Let me come up with one. All right, let's do, I'm gonna do something real quick. Since the Olympics are coming up, let's do this one. I just looked up the an Olympic-sized swimming pool. An Olympic-sized swimming pool contains approximately 660,000 gallons. So that's what an Olympic swimming pool has. Let's figure out, it's always fun. Let's do it for a normal bathtub. And if you go in, and most people, most of us have an idea of what a normal size bathtub looks like. But if you go in and you actually go look and type into Google, I will tell you it has changed over the years because of water conservation. A normal bathtub, according to lovely Google right now, is 80 gallons. But I'm pretty sure that 80 gallons is if you filled it all the way up to the top and to the brim, but most of them have a value. And so the typical number that I use for bathtubs is 72 gallons. And that's if you fill the bathtub. So if we want to estimate the number of bathtubs in an Olympic size swimming pool, I'm going to have, there's my 660,000 gallons. And now we're going to do a conversion. I've got one bathtub to 72 gallons. And again, that's a number I'm not going to be able to do in my head at this time of day. $668,000 divided by 72. It's about 9,200 bathtubs. And you certainly wouldn't want to carry this out more than two significant figures because it is an estimate. It's a total estimate. So one of the homework problems that you're going to have to do is dealing with an estimate. It could be breaths in a year, could be number of pages, number of pages of paper in a ream of paper if the average paper size is X. And the whole reason we do these estimates is so that we can give ourselves a back of the envelope. Does that number make sense? And I usually like to do is if you go out and read the newspaper and somebody says, oh my gosh, there was an accident and they spilled 550 ounces of this stuff. And you go, okay, what's 550 ounces? Let's see, 550 ounces. If I do ounces to a gallon, one fluid ounce is 0.007 gallons. 64 ounces is the same as 1 gallon. No, 64 ounces is a half a gallon. So if I did 555 ounces, I probably did, let me do that calculation. $555 ounces divided by 64 times 2. That's about 17 gallons. That could be a big number or a small number, depending on what it is. But if I'm dealing with a news story, I want to make it sensational. So I'm going to blow it out of proportion and I'm going to use a bigger number. And we have to go and say, does that make any sense? Is that really a big deal? For example, when I was working environmental, EPA came out and said, you are sending too much pollution. Your plant is sending way too much pollution into the atmosphere. We couldn't argue that we hadn't had some problems, but when we actually calculated the amount of pollution that they were arguing and beating us over the head about, it was less than one car on the highway that drove by the plant per year. So I was right by I-15 where we had thousands of cars drive by the plant, and it was less than one car is what EPA was arguing about. Totally legit argument. Not saying that it wasn't, but when you put it into perspective, you can see where you're having that discussion of, is this a big problem or is this a small problem? Is this a big number or is this about not as big number? So what we're going to get into is we're going to use SI units. So we're going to use meters, kilograms, seconds, all of those lovely units. We're going to talk about derived versus fundamental units. We're going to work with those. And as we start getting into the rest of the week, we're going to start talking about one-dimensional motion, and we're going to introduce the word vector. Depending on what algebra textbook that you used, you may have never seen the word vector in your math books. But all a vector is it has direction and magnitude, and many of you have worked in vector notation and just didn't know about it. But physics, direction is important, and we're going to talk about terminology. So I'm going to stop there because I've covered quite a bit of what's in chapter 1. You have extra videos that are out there, and I want to give you an opportunity to make sure that you get into WebAssign, get that going. Make sure that you get an opportunity to do your estimate of the number of baseballs in a 55-gallon drum. And then I will sit here for questions for anybody else.